timber columns. We already taken one examples, detailed examples on the timber columns. So the example is load bearing wall is a part of shop to be constructed in Melbourne. So we have a load bearing walls, and it's part of construction in Melbourne and it's shop. It consists of visually graded 120 by 45 by 300 meters, so it's 3 meters long, and it has this 120 millimeter depth and 45 millimeter width. That's the timber beam is given to us. Long season pine is F8. The grade is F8. That is given to us, and at start at 600 center with 3 rows of nogging. So there is another center to center distance 600. Each stud is to be fixed at the top and bottom plate by 2 screw nails. So they are fixed at the top and bottom by the screw nail. By typical stud, find the compression capacity under the permanent load only. So we need to find the capacity NDC, compression capacity under the permanent load. I want to solve these examples. Let me help you out with this example. So there is a clause that we're going to use, clause 3.3.1.1. That clause has a compression strength capacity NDC is equal to 5 K1 K4 K6 K12 FC dash AC. So from the clause 3.3.1.1, the axial compression capacity is let's say it's represented by NDC 5 K1 K4 K6 K12 FC dash AC. All right, so these equations and the unit for this one would be Newton. Now if you really don't know these equations and your standard is not there and you are sitting with the architectures and you just want to have a 30-second give it to go and find the capacity of these timber members, is quite simple, because as you know, when you have a timber beam under the bending, like I am just revising the one that we have a lecture notes, you have a timber and let's say you put this loading on these timbers. Let's say you have a loading on these timbers. Under these loading conditions, your timber will going to bend in that fashion. So bending meaning that you have this part is under compression and this part is under tension, meaning that you have a neutral axis that will dividing your compression part and tension part. Now if I want to know the bending, so you have this bending, let's say this is compression part and this is tension part, and if you want to know the bending stress, how much stress that is applied due to the bending moment M, that bending stress can be found by moment that you are applying over Y times Y over I. So that is the bending stress equations, and then sigma B, that is the bending stress equation. But the same timber that I show it to here on top, the same timbers, if I can use it and I just try to squash it, just apply the compression force like this, same amount of compression force. So for that compression force, let's say sigma A, axial stress is equal to load, the load that you are applying divided by cross section area, that cross section area of this part. So that is the axial stress. Right, standard has a different terminology for that stress. They saying FC dash, so that's we going to use FC dash. This load, they are just putting the load as a NDC, that is the notation NDC, and area they just put the AC as the area, this one. So if I just want to calculate NDC based on our basic engineering equations, it would be FC dash times AC. And if I want to know F8 FC dash, because the grade F8 is given, you can go on the appendix. If you go on appendix, If you go on appendix and you have F8 grade and FC dash would be 18 megapascals given here, table has 2.1. So from table has 2.1, FC dash will be 80 megapascals, which is Newton per millimeter square. So 18 Newton per millimeter square times by the area. Let's take an area. I'm not considering anything like seasoning and unseasoning. It's just 120 by 45. So area equal to 120 millimeters times by 45 millimeters. It gives me, let me try to find that, 120 times 45, you get 5400 millimeter square. So times by 5400 millimeter square. In that case, 18 times 5400, you get 97,200 newtons, which is about 97.2 kilonewtons. So if you don't know anything, basically from your from your year one, you are still in the positions that your capacity of the timber section is 97.2 kilonewtons. Of course, this is not correct. Meaning that we need to take into account these capacity factors and these 4 Ks that we are sitting here. But at least we have indicators. Meaning that 97.2. So at least in your back of your head, you need to keep in mind that you have 97.2 kilonewtons. It could be reduced by some amount because of those factors. So keep in mind that we have 97.2. So let's start with our example 5, K1, K4, K6, K12, FC dash, FC dash AC. Now in this case, we will have a this is given in the clause 3.3.1.1. I can show it to you again here. That is clause 3.3.1. We have these equations K1, K4, K6, K12, FC dash AC. Now in this equation 5 is given capacity factors, and that is given in clause 2.3. So 5 is equal to capacity factor, and that 5 capacity factors can be found from our clause 2.3. So let's go to the clause 2.3. Clause 2.3 capacity factors. If you turn the page over, on that page you have a table 2.1 and you have table 2.2. Table 2.2, we use it for joints. We don't need to worry about these tables because we are not working on the joints. We are just our subject is related to the members only, so we always use table 2.1. Now in these tables you have category 1, category 2, category 3. I will revise it again. I have done this one multiple times. Probably this is the 4th time that I'm revising it. That category 1, where your member is not primary members, it is a secondary member. Meaning when it goes to the service, and if it fail, then only 25 meters square, not more than 25 meters square area will be affected. Meaning that if that particular member fail, only the area 5 meters by 5 meters area would be damaged, or the users in that area. So basically they're saying that your users will not be affected much if you are in this category. There is less safety risk on category number 1 members. So in that case, they are just recognizing that your penalty is low because you have 5%, 10% penalties that standards wants to recognize. That is okay. So you have 5 to 10% penalty. Then you come in the category number 2, which is kind of considering more safety. More safety meaning that this is a primary members. If that members fails, you have a reduction up to 30% penalty to 15% penalty applied to your design. So category number 2, where you are designing the primary members and that members fails, your structures would have more than 25 meters square of area will be affected. Category number 3, which is the, again, this is the most severe case, where you have a primary member again, but that primary member is sitting in the one of the hospital or police stations or fire station or thermal power stations, the critical structures where if they fail, they can't help to the community, right? So they want to have a more security here, more safety here. For that safety concerns, they are applying more penalty, more reduction, up to 40% reductions is applied here. Now in our examples, I think generally all the columns are primary members. Does they mention anything about primary or secondary members or something? A load bearing wall constructed, it consists of visually graded season, center to center, each stud is to be fixed and bottom distance. For typical, find the compression. No, they did not mention anything, but most of the time the columns are the primary members, because you can think of when the columns comes out, they will going to take the beam will also fail. If the beam fails, so your area affected by that would be larger than those greater than 25 meters square. Affected, it would be primary members, because in these cases particularly we have a load bearing wall. So therefore we classifying as a primary members. From table number 2.1, we can say that is a category 2. We classify as a category number 2, and in this one F8 grade, if you have higher grade you have less penalty, but all other grade you have a 30% penalty. So we take it 5 equal to 0.7. So 5 equal to 0.7 because we have F8 timber grade, category number 2. All right, so first one done, 5. Now second one, K1. What is the name of the K1? And by the way, this K1, all these K1 is called modification factors. That group of those K is called modification factors, meaning that if you come back here and if I just group them all in the one box, it will be called as a modification factor. Of course, it has their own name, but they have a modification factors. They have own specific name. Now the first one has a 2 options. First one, K1, has a 2 options. 2 options meaning that the name of that one is called duration of load factor. That is the name that I just take it from here, table 2.3, duration of load factors. You have 2 options. Either you have these options for the strand of timbers or for joints. We not worry about joints, we were just going to take it member. So these tables can be used if you are talking about the probability of occurring the ultimate load onto that timber members for specific period. Less safety concerns, if you think that your members are require more safety and need if your members are loaded more than you think, then you go for 5 months and 50 years. In normal cases, in normal structures and normal situation, we generally go for 5 days. That is the probability. Again, this is based on engineering decision and based on the client requirement, how the members are loaded. Is it loaded for the full life of the members, or it's just going to load it for this one? Now where you going to get this info from? Your architecture and surveyor generally give you these informations, how your beam and where the beam would be serving, right, where it going to be located. So then in that situations you can use one of these factors. There is another options as well. If you go on the appendix, one of these appendix, let me find that appendix. There you got appendix G. In the table G1, you have different load cases are given. In normal situations or in the practice, you need to analyze all the load cases. Some of the load cases you can eliminate based on the situations. If it is not wind sensitive structures and so on, you might not consider the wind and earthquake loading. but most of the times you need to analyze all the load cases and you need to find the critical load cases. But for us, it's in a shop, so therefore we say they already recognize that okay, it has a critical load case is a permanent loading. So in that case we have a permanent loading case. So if we have a permanent loading case, this is the permanent loading case. In that case you can take 1.35 G, that is the load case. We no need to worry about this one, but we're going to have a load duration factors K1 equal to 0.57 coming from table G1. So from table G1 we have a, in the examples is given permanent load only, and that is 1.35 G. In that case load duration factor K1 equal to 0.57 coming from table G1. So we done 5 capacity factors, we done K1. Now we're going to go for K4. Now K4 equal to K4, we have these situations here. In that K4, in this K4, what is this K4 called? You can come back here, and the K4 would be here. If you turn the page over, K4 would be partial seasoning factors. So K4 is called partial seasoning factors. Partial seasoning factor. Now K4 is partial seasoning factors. In these situations, we have given the seasoned timbers. Where is written? Let me find it out. It says that seasoned pine F8 dot. So it is seasoned timber. So it is given seasoned timber. So for this case, seasoned timber, we can have a seasoned timber. For seasoned timber, generally K4 equal to 1, so we can go for 1. Where seasoned timber is subject to a condition in which average moisture content of 12-month period is expected to exceed. So your suppliers will going to specify that if you are, as I mentioned, if your timber is exposing to the rain and it's sitting outside of the structures, I think this is load bearing wall, so they are sitting inside. When the timber goes onto the service or column goes on the service, it will have a less chance of come direct contact with the rainwater, or they are just having a humidity coming from the air. That's not that significant. For that case, your moisture content would not exceed 15%. In some situation where if your EMC increase by 15%, in here, if you have more than 15%, let's say EMC is given to you, let's say someone give you EMC, let's say 25% EMC is given. EMC means equilibrium moisture content. So let's say 25 take away 15 divide by 10, so that is 1 only, so that is not good. Okay, 25 is just 1, so there is no issue. So more than 25% only, so let's say 30 take away 15 over 10, 1.5, 1 take away, what is happening? Oh, you need to times by 0.3, sorry. So let's say you have a 25%, 25 take away 15 divide by 10 times by 0.3. So 1 take away 0.3 is 0.7. So 25% give you 0.7, that is 25. If you have a, let's say 30 take away 15 divide by 10 times by 0.3, 0.45, 1 take away 0.45, it gives me 0.55. So in that case you take it 0.55 or greater. So you can't just take it more than 0.7. So it's just, they say that maximum equilibrium moisture content would be 25, because you can see if I put 25 here, then it gives me 0.7. So you cannot have a moisture content more than 25. because then it will restrict this one, because you can't just take it 0.6. 0.7 is the ultimate K4. So if someone give you the equilibrium moisture content, don't hesitate to use in the case 4, and I already show it to you how you can use it. The equilibrium moisture content is just 25%. If it is more than 25%, straight away you take it 0.7, because these equations will give you less than 0.7, and this wording is restricted me to use this one 0.7. It could be more in case if you have unseasoned timber and then it's drying it out. Okay, so that's here in this table. So in any situations you should be able to extract this K4, but in our case let's take K4 equal to 1, because we have a seasoned timber, and that is, you can read it from the clause, you can read it from clause 2.4.23. that is, you can read it from clause 2.4.2.3. All right, so far so good. Any questions there? Capacity factors. In any situations coming to you, you are in the positions to read the capacity factors. Don't be worried. I think I already not only discussed the ones that particularly attention to these examples. I already discussed how in situations where you can read the capacity factors. K1, I have given you the two tables, and in any situations you are able to read the K1 value using two tables. K4, you have two options, on season timber and season timbers, and for both of those clauses I have discussed with you. Now K6 was quite simple, because it's not that hard. K6, the name of that factor is called temperature factors. So let's write it down, and that is in the clause number 2.43. that is called temperature factor, and that is given in the clause 2.4.3. Now these temperature factors are specifically applied. You generally take K6 equal to 1, except where your season timber is used in the structures erected in coastal region of Queensland North and all other region of Australia North and 16 degrees Celsius modify factors, or you can take K6 equal to 0.9, 10% penalty is applied. But in case this is not the case, look, this is for your explanation only, because this other standard, which is AS3600, has given you this these figures there. Probably next year we're going to teach you this one, but you don't need to worry about it. This is just for your information. The Bureau of Meteorology has given the rainfalls for all Australia, and the standards recognize that one. That if your timbers sitting in this, look, this hex line, the diagonal line, which is classified as a tropical region. Tropical regions meaning heavy rainfall. So in this part of Australia will falls in the heavy rain walls. Only this part of Australia will have a heavy rain, like Queensland and all these Darwin portions here. This part is, so if you are designing your timber in this region, you would need to take K6 equal to 9. And it's not a rainfall. I think the rain is not the worry about, but this can also be used as a temperature. Okay, and these regions and here you don't need to worry about. But this is typically, we have a high temperature zone. I can say that this is the high. The rain one is not affected by the K6 does not recognize the rain. The I'm talking about this portion is has a high temperature zone. So that is K6. In our timber columns is located in Melbourne. So you can see that they have a shop here where they talk about this Melbourne. In those Melbourne region, you don't have K6 would be 1, because timber column is located in Melbourne, and Melbourne does not falls in this high temperature zone. North side of the Australia is the high temperature zone. So that is K6 coming from close to 0.4.3. Now next one is a quite challenging one, which is K12. what is that called? K12 is called stability factors. Stability factors. And what is stability factors physically, that I'm going to tell you. So if you come back here, look, there are two stability factors. Don't be mixed up when you are working on that one. The one stability factors that I am going to show you, that is for beam. That is stability factors, that is beam, close 3.2.4, and rho B. Rho B is the one that you, rho B and S1, that is the stability factors. Now this rho B and 1 stability factors, that will be used when you have beam and they do this lateral torsional buckling, kicking it out from this original position. That was the lateral torsional buckling, and we have restraint like this one to prevent that one. Okay, so that standards recognize that. This one not happening, this one, but this one would be intermediate, and that would be quite severe. So that's for beam. But for here, you don't need to remember but that which clause is for what, because I think in your, when you go to that clause, design for in that clause, I think here K12 is clause 3.3.3. so that's 3.3.3 stability factors. Stability factor is here, that is for the columns. Now that is for columns, meaning that if you have a columns like this vertical, and if I do this one, it should do this one. Look at that, it does this one. So if you have a short columns, it will not going to does this global buckling. This is called global buckling or stability issue. This is the intermediate columns. This is intermediate columns, and this is quite long columns. Okay, so this is how, by looking at the columns, you can't just say that this is short columns, intermediate columns, and long columns. It has a consideration of how the restraints and how these factors are affecting. So it has this multiplication rho C times S, and rho C is quite simple to calculate, which is called material constant, and these material constants take into account the creep, shrinkage, and the grade. What is the grade you have? So you have seasoned timber and unseasoned timbers in that case. Now let me go and find out this rho C, that we have F8 grade. Let me find it out. Rho C first, material constant. So K12, we need to first find this rho C times by S. What is the name of rho C? Rho C is called material constant. Material constant. And where are you going to get the detail? You're going to get the detail from table number 3.3. And I will show you that table again. And for that one, we need F8 grade given in our examples. I can show it to you. That is given in our tables is a F8 grade. And then we have a seasoned timbers. I think they have given the seasoned timber here. So for that case, we have seasoned timber F8, and we have a seasoned timber, right? So in that case, we will have these tables, seasoned timber, and you have F8. So in that case, rho C equal to 1. So let's say rho C equal to 1. 1 meaning what does it mean? How useful they are? Look, this rho C, I want to physically explain this situation, saying that what would happen if the rho C goes 1.17. So if it goes 1.17, then you are going to fall in this category, which is not good. Look, this is good. This is not good. Your column will going to have a global buckling. So meaning that F34, these higher grade, have these seasoned timbers, they have a material constants higher value, and unseasoned timbers, they were even quite severe. You can see if you use the low grade one like F17, F5, you even have a lower this rho C factor. So these grades are quite sensitive for the global buckling, as you can see here. And then you need to calculate this S. Now S requires some kind of explanations. So rho C, that is coming from table number 3.3, and I already explained you that. Now S, what is the S called? S called slenderness coefficient. Slenderness coefficient. Now where this name come from? The slenderness coefficient, if you just come back on here, that is a slenderness coefficient for lateral buckling under compression. Now this S has a two parts. One part is the buckling about the major axis and buckling about the minor axis. Now someone might say what is major axis and what is minor axis. Now the standards will tell you this one, that slenderness coefficient buckling about major axis, and that is recognized by S3. When you see the letter S3, they are talking about slender coefficient S3. When you talk about the slenderness coefficient buckling on the minor axis, in the minor axis you have S4. That is the name for those two. We always do the two checks, and the S would be maximum of S3 and S4, right? And the S3 and S4, what is S3? S3 is a slenderness coefficient, slenderness coefficient for buckling about major axis. Now what is major axis and minor axis? I will explain it now. S4 slenderness coefficient for buckling about minor axis. Now what is that major and minor? So if I draw, now generally these timbers members are rectangular members. So if I draw the rectangular members here, which is the width and depth. So let's say this is the kind of a members. I think just draw a little bit. That can, okay, so you have this B and this is D. Now if I draw the line which is parallel to this D, which is y axis, and if I draw the line parallel to this B, which is x axis. Now this x axis is the major axis. You don't need to remember, I will show you where they are, and this y is your minor axis. Okay, that's what the vocabulary they use. Now major axis meaning that if you don't have restraint, it's difficult because you have two options. You have two options meaning that, let's take this is a ruler and this is a rectangular cross section. For these rulers, it is very easy to do this. You can see, and this is y axis, minor axis. This is minor axis, physically minor, because you are bending about this axis, y axis, right? Bending about this y axis. So this minor meaning that you will have this buckling. Now let me draw this blue one. You will have a buckling like this, right? So you can see this is a minor axis and it is easy to buckle. It is very easy to buckle about minor y axis, right? For the same thing, if I want to do this same one for the same sort of columns here, and let me think that okay, you have this x axis, which is your major axis, and this is y, this is minor axis, and someone wants to bend like about this x axis, this line. Let's say someone wants to bend these lines and these lines like about this x axis, like this. Someone wants to bend like this. It's very hard to bend like this, right? I'm talking about not this way, but just this way, just this way, like this. It's not easy to buckle this way. It's a strong axis, it's a major axis. So the reason is like that. If you don't know how to recognize that, when you draw the axis and your materials spreading from that axis is small, then use minor axis, right? It's easy to do this one. If you draw the axis and materials are spreading far away from the axis, it's difficult. Spreading meaning that if I have this, here you are, so we have loaded now meaning that if you have this timber, and you can think two ways, that look at this. you have this minor axis, let's say YY minor axis, and if you want to see this area, spread it from the minor axis. This is the area that is coming from that YY axis, and let's see, this is the area that is coming from that YY axis. You can see this is kind of, let's say, A and A. In similar way, if I draw the same one here, and you can see this x-axis here, which is the major axis. Look at the distance from this. This is the area that are spreaded from that axis. So if you want to look at this B, look at this. B is greater than A, right? The area that the materials that are distributed far away from this one. So it's difficult to bend. So it is hard to buckle about x-axis, meaning that this is a major axis, and this would be your minor axis. Is easy to buckle. I hope you understand this. It is easy to buckle. So if you have an options to put the restraint, then you put the restraint about this YY axis. Okay. So when you how you going to put the restraint here? So you put the restraint perpendicular to this. Let's say you put the restraint here. If you want to stop this, you can put the restraint like this. You put the restraint like this, right? That is the minor axis restraint, meaning that your beam will not going to do this one, but it will have this kind of buckling. So it is difficult to buckle. So as you can see, this is the prevention of that buckling, because otherwise it will do this one without restraint. If you do the restraint here, put the restraint here, put the restraint here, and put the restraint here, then it will does this one. So it is easy here, easy to buckle. But when you put the restraint, easy to buckle. But when you put the restraint, it is getting hard to buckle. So I hope you understand that, right? So this is the minor axis buckling, and the restraint. And if I want to put the restraint, I would put the restraint like this. This is the major axis restraint. That is your major axis restraint, meaning that these portions that you can see, they will not going to have this buckling like this. This is the without restraint, but with this one it will have these bucklings, right? So same way like this. All right, so I hope you understand this. Now can you please someone tell me, look at this, look at this diagram. So let me put these diagrams, copy, and you need to help me out. Just an exercise that we're going to play. Copy, and we're going to put it here. Paste. Now, now by looking at these figures, what kind of restraint that we have? Because look at that, only one axis has been restrained, right? Do you think is a minor axis restraint or major axis restraint? Minor axis. Let me check. Is it a minor axis? So you have when you have a minor axis, you have this is minor axis, and this is your major axis, and that would be perpendicular to this one. You have this. You don't have about this one, so you can easily bend about this way. And yep, that is correct. That is a minor axis bucklings, because these figures also help you. this one, like this, like this, like this. That is the minor axis buckling. This is the minor axis, and perpendicular to this one is the minor axis. You have these restraints going on here. So you have a minor axis buckling, and generally, as I mentioned, minor axis buckling would be recognizable. So if you have an options, you can have, if I want to put the major axis restraint, how do I'm going to put it? Let me put, if someone can help me, if I want to put the minor axis, so this is the, let's say, if I want to put the restraint on the major axis, I would put like this. Sorry, I can put the red one. So I would have attached to this surface, right? I hope you understand that. Like this, like this, like this. That is my major axis, and this is going attaching to this small part. This is going to attach on this small part, and this is attaching this one. So I hope you understand that. That is the major. It has not given major axis restraint, and this one is minor axis restraint. All right, so now you know the difference between major and minor axis restraint. So from this figure, we have minor axis restraint, meaning y-axis restraint. We do not have any major axis, or say x-axis restraint, right? I hope you understand that. So let's work out first, because for S, which is the slenderness coefficient, would be S3 and S4. Let's work out the major axis first. Major axis, because standards has this major axis first. Like in the closed, there is no matters which axis you're going to work first, but you have this major axis, which is your x-axis, LAX on D, and S3, G3 on L on D. Now on here, you need to take the smaller of these two. So it says that if you want to calculate S3, you will take minimum of LAX on D and G13L on D. Now basically, how I read this one, that is coming, by the way, from clause 3322, right? Let me write it down. That is coming from clause 3.3.2.2. Now, by the way, how I read it, the reading would be that you have major axis restraint, then you can use these equations. The S3, if you have major axis restraint, meaning you have this LAX, meaning that you have this red part, or which one, the red parts you have, then you use this first equation, LAX on D. If you don't have restraint, but still some kind of restraint comes from the end meaning that you can still provide the restraint by holding it at the ends. You still provide the restraint. So the standard recognized that by putting the G13 in front of this L on D, saying that how your ends are connected, that will also give us whether you have this global buckling or not. So there are two equations. One, these equations I can say with restraint. This equation I can say without intermediate restraint. Let me put the word intermediate restraint. There are restraint. Of course, both of has restraints. Some end restraints. So this one with intermediate restraint, meaning middle restraint, and there is no any intermediate restraint, just the end restraint. So that is this equation. Now in here, major axis we don't have any restraint, right? Major axis we don't have any restraint. So in that case, we can just cancel that. We don't have any restraint. So let's say we just go for this G13 L on D. Okay, So on that case, G13. Now this G13 require bit of explanations. Now this standards is not helping me. There are 1, 2, 3, 4, 5, 6, 7 and 8 different cases. 8 different cases means how your timbers are connected at the end. How these top end and bottom edge are connected to the other members. That is the based on that connections it has given you different G13. Now let me explain you that G13 story that that from this one of my reference here that will be quite useful to read together. So you said I'm not specifically mentioning this G13 for these particular examples. I want to have a knowledge and skills to use table number 3.2 for any cases. Okay, if you come across any cases, you should be in the position to extract a G13. Now stay with me. I will going to explain you this in a way that you can understand. Now there are 8 different cases. First, I will classify those 8 cases into 2 separate classifications. Now 2 separate classification is the there are 1, 2, 3, 4, 5, 6 cases. There are total 8 cases by the way. Out of 8, there are 6 cases where you have brace columns or brace columns, or you have a sway column or unbraced columns. You can also call unbraced unbraced columns. Now what is the sway columns, or what is the brace column, and what is the sway column or unbraced columns? So let me write it down. So first I like to explain what is brace columns and what is, let me explain you the word brace column or unbraced column, or standards also say that is a sway columns. Right? That is also the word. Now what is brace columns? So let's say you have a timber columns here like this in the frame, right? These are your columns. Now in that columns, let's say you have these foundation here. Let's say these columns are connected some sort of wall here, so rigid wall. And if I apply some kind of a horizontal load, if I apply the horizontal load, in that sense, these nodes that you can see, they will be staying in the positions. They are staying in the positions, meaning that they will have some kind of deformations, but these deformations would not be like out, that points will not gonna come out, right? But let's say this is a brace columns, by the way. This is the kind of a classification for brace columns. Let's say I have a system where you don't have this wall. I don't have this wall. In that case, let's say these nodes are here, and let's say I'm applying this horizontal one. In that case, these nodes will go, not that kind of things, but they will move out out like this, right? They will, under this loading condition, they will just going to go. So that is called sway column, right? In that sway column, because this is fixed, so it will not gonna go, but these portions will come here, these portions goes here, these portions goes here, and so on. So you have a sway columns. That sway columns is that so I hope you understand brace columns and sway columns or unbraced columns. So there are cases for brace columns. There are 6 different cases for brace columns. Now let's start with the brace columns first, which is the flat end. Flat end, you have a flat end. So you come here, read with me. Flat end, both ends are cut square to the longitudinal axis and bearing on a hard surface. So let's say you have this flat surface. You can see this is flat, and it's just like columns, and it's just fixed. There is no any rotation, there is no moment. It's not going in this direction, it's not going up and down, it will not have a rotation this end. So that would be good. So you have this 0.7 if you have this flat end kind of restraint, which is 0.7, and that is part of the brace columns. Brace columns mean these joints will not going to move. Okay, so I hope you understand the flat end, and in that case you take 0.7 as a G13. And by the way, how it's going to help, because the lower this one, which is good. If you put this higher number, because this S3 would be larger, then we will have a trouble. So lower number is good. Smaller, we try to get this smaller number, otherwise the penalty will be given, because if you put this G13 higher number, S3 will go high, S3 will go high, S will go high, and S will go high, we will have this K12 smaller number. So we keep in mind that we're going to have a construction, or we can have a columns end in a way that we will keep these numbers as small as possible. So this is a flat end. This is physical meaning of that tables as well. I hope you understand. Flat end is a part of brace columns, and flat end has a factor 0.7. This is the pictures that I'm just showing you. That is a flat end and it's a 0.7. Now the second one is restraint at both hand in the position and direction. I will explain you what is position and what is direction. So it has again 0.7. These are kind of a same situation as I mentioned. This is 0.7 because it's fixed. It's not going here, it's not going anywhere. It's kind of a fixed end. So same way you have both hand restraint in the position. So you remember there is a fixed end columns, right? So if you have fixed end column, you have 0.7. Is by the way like that. So if your columns is part of brace columns, and part of brace columns meaning that you have this end fixed, this end fixed, in that case your G13 equal to 0.7, which is good, by the way, you have only up to 0.7. So the winner is 0.7 fixed, right? If you don't have fix, your penalties start coming in, because you can think of physically in a way that if you have a fixed end, then it's hard to buckle. You can see it's difficult to buckle. It will buckle, but it will take significant amount of force to buckle. So 0.7 good. I like 0.7. The way it start increasing, I'm start worrying for the columns. Start worrying means the standard start applying the penalty. Now, so I hope you understand these two, which is your fixed end, and this is part of brace columns, by the way. Now, the third case is each end held by two bolts substantially restrained. You remember that you have this bolt on the lectures. We have 0.75 is kind of a I think pin. So you have this two bolt. So both hands held by two bolts equivalent restraint. So it's kind of a fixed, but this bolt kind of sometimes have slight rotations. It's not showing it here, but it is not a rigid, it is not rigidly, but it might have very slight rotation. Therefore it's just putting a little bit extra 0.75. You can see it's close to 0.7, but it's slightly recognized that your bolt that you are putting it here at the two end, it's not kind of exactly the same that we're going to talk about those 0.75 things. So both handheld are by two bolts, and I hope you understand that two bolts 1.75. So this is again part of the brace column. So your columns will not be moving away from their positions. So there is 0.75. I hope you understand fix, and each end held by two bolts, some kind of rotation allowed. It says substantially restrained. Says you can see substantially restrained 0.75. Now next case again is the brace one. One end fixed in the position and direction, the other restrained in the position only. So 0.85. So it's kind of a fix and pin. So it's fixed no matter which one is fixed or which one pin, one of them. So one restraint in the both position and direction, which is this one, and other restraint in the position only. So position meaning, let me write it down. Position meaning displacements. The wording that they use is position. Position meaning that it's a displacement. What is displacement meaning? That if you have this point and this point, if it does not go left or right or up and down, then your this position is restrained. And so that is position. And direction, it means that rotation. Direction meaning rotation. That's what it says. Direction meaning rotation. Now that rotations meaning that this point can rotate in their positions about the axis, then your direction is trusted. So in that vocabulary it says that your direction other restraint is only position. So direction is not restraint. So you have pin. So by the way, this case is a fix and pin. 0.85. So 0.7 and 0.75 we get the partial little bit of rotation not allowed, that is G13.75 when you have two bolts. Another one is the pin. Let me put that pin like this. Let me put that pin like this, and you have fix. So you have fix end, but you have pin here. In that case, G13 equal to 0.85, right? So that is the 0.85 fix and pin. I hope you understand those four cases. This fix, this is fix, this is partially fixed, yes, some kind of rotation allowed. This is fix and pin. Now start in the light framing 0.9. Okay, here you go. Stud normally cut square and bearing on a timber top and bottom plate. So it's kind of a screw nail. So if you have kind of a screw nailed one, and it's recognized some kind of not there might be some kind of rotations allowed, and screw is not kind of a bolt. So you have this 0.9 for this stud in the light framing structures, which is 0.9. Now this is good. This is getting worse. Okay, 1 and 1.5. Restrain at both hand in the position only. So it's a pin is 1. So this one both hand for restrain in the position only, pin connection. So if you have pin like you have one bolt only. Look, if you put two bolts, that will allow to have some kind of rotation. But if you put one bolt like this, if you put the one bolt, you can rotate easily, right? You can rotate easily. But if I put the two bolts like this, if I put two bolts and two bolts, let's say 2N, it is not easy to move. One bolt is kind of pin, you can see. If I put two bolts like this, it is difficult to rotate. It still rotate, but it's difficult. So that's recognized by the standards. And this is two bolts, so it's one. So I hope you understand these two bolts. One bolt is pin, like a restrain in the both hand in the position only, like a two bolts. So it's a pin one. So you have pin one bolt one. So if you have a one bolt, then you have pin connection. Restrain at one end in position and direction, and other end partially. So now this is coming to the sway frame or on brace. Now we are part of that. Your one end is fixed, but another end is moving away. As you can see, this moving away. So restrain in the one end direction. So that is bottom one. And other end partially restrain in direction, but not in the position. So rotation restrain, but position is the displacement is happening. So it's 1.5. Very worse. They don't like this one. This is even the worst one. You never want to do this one because just two. So restrain at one end in position direction, but not restrain in either position or direction at other end. So you have this kind of pin, and its rotation, displacement, everything is happening. This whole part is moving. So therefore is a higher penalty here too. So unmute yourself if you don't understand these tables, or you don't understand these 8 cases, how you going to read it. All good? Okay, so that's fine. I think for our case, we are in the start in the light framing. We are going to take this 0.9. Start in the light framing, meaning that we have this stud normally cut square and bearing on a timber top and bottom plate. So we have this kind of a screw nail, and this one 0.9 that we going to take it, and we have this brace columns case. So we're going to take these light framing structures, the dimensions, anything load bearing walls. So I think it's part of light bearing structures, and they have fixed at top and bottom by two screws only, two screw nails. and the typical stud, find the compression capacity under the permanent load. So let's say we have this G13 equal to 0.9. G13 equal to 0.9 because we have studs in light framing structure. That is from table number 3.2. So now once you have G13, we can calculate S3. S3 is equal to G13L on B. G13L on D. G13 is 0.9. L is 3000 given in our figure, I believe. This 3000 is given. That is here. 3000 over small d. Now small d is given in our example, which is 120. Which is 120. So you have 0.9 times 3000 divided by 120 is equal to 22.5. So S3. Now S3 is done. Now S4. S4 is a minor axis buckling. Now for that one, again we're going to move on here, and S4 has a LAY on B and G13L on B. So S4 is minimum of, and by the way this minimum is written here, taken lesser of following. By the way, just recognize whether you have restraint or not restraint. LAY on B, or you have G13L on B. Now this portion is going to tell me, this portion is saying that you have restraint. You have restraint and you have do not restrain. Right. So and we know that minor axis is restrained, right? This minor axis is restrained by this green one. So if you have a restraint there, then we're going to use this this restraint equation, which is G13. No, that is without restraint, but we have this LAY on B, which is your S4. LAY is LAY. How are we going to calculate LAY? So you have at 1, 2, 3, and 4. So I think 3000 over 4. So that will give me that 750. How do we know this LAY? If you come back to this figure here, that will going to tell you LAY here. You can see this is LAY, and LAY. So that LAY going to be 750. So let's put the 750 millimeters over B. B was 45. B was 45 millimeters. So 750 over 45, you get 16.7. So S would be maximum of S3 and S4. So S3 is 22.5, which is your major axis buckling, and this is your minor axis buckling. So basically this is telling me that which axis will buckle cost. So as you can see, these minor axes, major axes are the wing. It will have a, because it does not have restraint. So S equal to 22.5, and we need to multiply rho c times S, and the rho c we already get it, I think, from the tables. Where was that? We take a notes about that rho c, right? Yeah, here 1. So let's get rho c is helping times 22.5 is equal to 22.5. So come back here. If it is less than 10, we don't have any global buckling, short columns. If it is 10 to 20, you don't have intermediate columns, and this is kind of a bad one, that is greater than 20, and we have 22. So we need to use K12 200 over rho c S square. So K12 equal to 200 over rho c times S square. So you have 200 over 22.5 square. 200 over 22.5 square. You get 0.4 as a K12. Now K12 we got it. We need to find FCDS. I think we already find FCDS was, remember that FCDS we got it. Where was that? FCDS was, I can show it to you again here. FCDS was 18 megapascals. So FCDS 18 megapascals. Concrete compression strength, timber strength. So FCDS is equal to 80 megapascals. That is, let me show you again. There you go. These tables, table hash 0.1 F8 FCDS 18 megapascals given here, and that is F8 here, and that is 18. So that is table hash 2.1. Area is given 120 millimeter by 45 millimeters. We already calculate that one, but let me calculate that. 5400 millimeter square. So AC 5400 millimeter square. So now let's get the NDC equal to 5 K1 K4 K6 K12 FC dash AC. 5, how much was that? About 0.7. I remember that. Remember category number 2 and so on. So you have 0.7. Let's read K1 as well along with that one. So 0.7 and K1 is 0.7 and K1 is 0.57. So K1 is 0.7, 5 is 0.7, K1 is 0.57. Let's read K4, K6 together. K4 is 1, K6 is 1. So K4 is 1, K6 is 1, K12 we just found here somewhere. K12 was 0.4, K12 was 0.4, FC dash we found 18 Newton per millimeter square times by AC is 5400 millimeter square. So let's put in the calculator. 0.7 times 0.57 times by 0.4 times by 18 times by 5400. So you get 15513.12 Newton. That will just give me 15.5 kilonewtons. So that is your final answers, but I like to have a comment with you. Look at that. If you are a first year students, he might argue that how come you got answer 16 and my answer is 97.2, right? That 97.2, because without that timber theory, we have a 97.2 NDC, 97.2. But when you take into account the K12 stability factors, your timber will going to buckle, because you have this K12 was troublemaker 0.4, K6 was not, K6 was good, no problem, K4 was 1, no problem. This K1, I think the permanent load, so there was 30% penalty here, about 60% penalty here, and so on. So it's kind of not helping. You have some penalty here, so they are quite challenging. Here penalty, here penalty, here penalty. These are not having any penalty. Three guys are making trouble. So as you can see, therefore from 97.2 you got straight away 15.5. so that is your answers. NTC 15.5. Unmute yourself if you have any questions there, and you tell me. Okay, now you are in the positions that if someone give you, yeah, I think next